All right.
Right. So the topic for today's lecture and the demonstration is the data analysis of fMRI. So in the third week, last week we talked about the pre-processing of fMRI data. And sort of to summarize that a little bit, right, after your data acquisition, there's a couple of steps that you need to do to make sure your data is ready for statistical analysis, namely the slice time correction, motion correction, co-registration of your structural and your functional images, the normalization of your images, and maybe tissue classification for VBM analysis, and then lastly the smoothing of your data. So once you've done all these steps, then you're sort of ready for statistical analysis, and which is the helps you to answer the research questions. I also talked a little bit about what sort of steps in this whole process you do, quality assurance or quality control, both in terms of the data acquisition to see if there's any artifacts in your data, and in this whole process of pre-processing your data, where to look if there are any errors or if there are any mistakes. But suppose all this went well and you finally smoothed your data and it all looks good, then you're ready for the statistical analysis. I guess sort of for today what I had in mind is to talk about two main topics in the statistical analysis. First one is to talk a little bit about the general linear model, which is sort of the main statistical framework to analyze your data. And the second part is the what kind of statistical inferences you make, and especially pay some attention to the multiple comparison problem. What kind of correction methods are there, and what kind of different approaches you have. I mean, there are a lot of other topics in statistical analysis that you could are worthwhile to discuss, but I think these are just two of the main ones. And again, the Coursera course of Martin Lindquist and the one of the books is entirely devoted to just the statistical analysis. So it's definitely, you could easily just have a course on it, on statistical analysis on itself. But these are the topics I thought to talk about for today. The main framework for statistical analysis, and probably what like 95% of, or maybe 99% of all papers used, is the general linear model, which basically says that you have like some observations y that you try to model with a variables x, and the fit of this model, often referred to as beta values, and then you left with some error terms, so anything that the model can't fit, and this error is always supposed to be normally distributed. It's a really basic model, and it's not only used a lot in fMRI, but actually in all of the social sciences are within this statistical framework. In fMRI, one specific thing is that the application of the GLM is what they call a mass univariate analysis, and we'll talk a little bit about it later. What it basically means is that you're going to run this model thousands and thousands of times, basically for one subject for each fossil, and I will talk about that a little bit later. But roughly, so this is the model, and it's all often in fMRI sort of visualized, and we're going to look at that later too, how the design matrix X here is visualized, and the observations, the data. And so, as you said, that you use this GLM at different levels, and the first, the main level where you use this is at the subject level. In this case, the GLM, the data that you have, your observations, are a time series, right? So you have you run some experiment maybe, and over time, and you acquire for each time point, for each volume, like one measurement per box. So that's the observation. Your model in that case is often referred to also as the design matrix, is just a specification of at what times did subjects see, in case of, I often use the example of phase processing, say an angry phase, a neutral phase, etc., whatever your experiment was. Right, so you're trying to model how well the presentation of these stimuli that you presented or whatever else they had to do fits the data. Your beta values, or often referred to as parameter estimates, can be thought of as sort of the amplitude of the bulk response. So it says something about how well any part of your model fits the data. And then what you're left with is also always some noise, some error terms. So you can ever really sort of perfectly fit your data. So I want to go over an example of how this GLM sort of works on a subject level. So I tried this really simplified experiment. So suppose you have like some block design where people see faces and houses and some sort of empty shapes, right? So just over time, suppose there are 6 blocks, so a face, empty, just a circle, some house, a face, a circle, and a house again, right? So that's the whole experiment. What you want to do then is sort of model at what times these stimuli are presented, which in this case just an on-off sort of block model. But this is sort of important always in fMRI, what they say convolved with the hemodynamic response functions. If you remember from the first lecture, we sort of know that at the time you present a stimuli does not instantaneously lead to an increase in the bulk response, but there is, due to several physiological factors, a delay, and it has this specific sort of shape of when the response peaks after the onset. And convolution, that means that you sort of try to incorporate that information in your model. So if you look at how that works out, is say, suppose you look at this upper panel here. This would be like a model for when phases are presented, right? So if you look at this black line, it just has ones when the face is presented and zeros everywhere else. Right, so here's the face, it's ones, here's all zeros, here's the face again, and then there's ones, and then zeros everywhere else. Now, you could use just to say this black line as a model for to sort of fitting your response, but by incorporating this information on the delay of your hemodynamic response, you get something that looks a little bit more like this. So it's basically it peaks later than the actual onset of the stimuli, and it also sort of stays on a little longer. Again, this is a step that you often do in setting up your model, so you're convolving it with the HRF. It's less of an issue in block designs. You might, if you look at this, you might see that this blue line overlaps fairly well with the black line, right? It's a little bit different, but not completely. If you start working towards like the event-related designs, where we have a lot more stimuli and a lot more different conditions presented a lot faster, making sure that you convolve the onset times with your hemodynamic response function becomes much more important. Because if you wouldn't do that, then your model would be completely off, right?
But SPM does that.
SPM does that, yeah. And same thing for, say, when houses are presented, right? You could do. And so you could have like one part of the model models these onsets of the phases, and then second part of the model could sort of model the onset of the houses. So you have ones here for when a house is presented, and zeros everywhere else. And you would convolve this sort of model with this href function to incorporate the delay in your human dynamic response, and you would end up with something like this. Right, so this is really simple model. You have sort of this blue line to model the activity related to phases, and this part to model the activity related to houses. And you regard like these maybe as just fixation or a baseline condition. So what you're then trying to do is, suppose you have this time series from a voxel, right? So that means the response over time in a certain voxel, say the amygdala, our favorite brain region, right? So it might look something like this. It's always quite noisy, so you have a lot of peaks going on, but you also see somewhat of a, or you might see somewhat of a response here already.
That's a super beautiful, nice voxel.
This is, yeah, it's a little bit of an ideal voxel. I added a little bit of noise, but...
You can find them, but that's...
Yeah. Right, so, but this might be the response of one voxel during this experiment. So what you often do in, how they often sort of visualize this is to turn this thing 90 degrees, and so you go here from point, say, 0 here till the end of your experiment. This is how often also in SPM, like your design matrix and your model is visualized. Right, so you have this response over time in a certain voxel, and your model then is, say, these two regressors. So this one was the regressor that models the onset of the phases, right here in red, and then the blue line is the model. It's the part of the model that incorporates the onset of houses. So you have these two parts make up the model, and then you have what you're trying to do is estimate these beta parameters. Basically trying to say how well does this model and each part of this model fit this my observation. So basically what you're trying to do is, and this is sort of not really how it works mathematically, but how you can think of it maybe is to say, I'm just going to see how well does this one part of the model fits this line, just overlaying it. And I've given here, say it like it fits this model maybe fairly well. It's quite some overlay, and I'm going to give this beta value, say 2. This is just an arbitrary number, but just to think of it could be something that's a correlation value, right? So you're trying to see how well does this first part of the model fits my time series. Same thing for the second part of the model, where you're trying to model the onset of houses. Again, trying to sort of overlay this part of the model to the time series. Say, well, how well fit does this fit the time series? And in this case, it doesn't fit it so well. So I would say, like, give it this second beta value at 0.5. And then you're always left with some error term, right? Because the model would never perfectly fit your observation. So you have some residual time series. Again, this is just like sort of a visualization. The mathematical background is a little bit, or quite different actually. And you're not really doing this. You're doing this whole model testing in one go. But this might be a way to think about it a little bit. So you've now tried to sort of have established what how well the model and each part of the model fits the time series. And what you then might want to do is say you want to test if the model and which part of the model fits your observations better. And we do that by using a contrast. So you use a contrast to test the differences here in related to activity. So you want to test whether these first beta value differs from your second beta value. And the way to do it is to use a combination of these beta values multiplied by a contrast, and then you divide that by your estimated variance. And that will basically give you like a t-value. So in this example, right, we have these beta values 2 and 0.5. This referring to the beta value related to the model for faces. This is the beta value related to the model for houses. You use a certain contrast, and the contrast is just like a weighing of these beta values. In this case, you would use a 1 for the first beta value and a -1 for the second beta value. And often this is represented as a contrast of 1 minus 1. And you just multiply these things, right? So you have 2 times 1 plus 0.5 times -1, right? And that leads to 0.15. And say if you have some variance of 0.3, then your test statistics or your t-value would be 2.7. This is a really sort of basic example of how this GLM at the subject level works. The important thing is to realize that this was only for one voxel, right? So this whole time series was just from one little voxel, and you're basically running this model for all the voxels, which could be 30,000. That's only like the in-brain voxels. The whole image actually has more, maybe around 100,000. So you're running this model at least tens of thousands of times. And of course, this all happens within SPM. And what it basically leads to are 3 types of images, which are now, and it's important always to realize that they're 3-dimensional now, not 4-dimensional. So right, the whole pre-processing and raw MRI data has not only the 3 spatial dimensions, but also a 4th time dimension, right? It's a time series. And basically what you're trying to do with this whole model fitting on the subject level is reduce collapse across this time dimension. If that makes sense, right? So you have this whole time series and basically reduce that to a value of how well your model fits this time series. This also means that, for example, if you look at your images on from your data, that these type of statistical images are a lot smaller than your raw MRI EPI images, just because they contain a lot less data. So there's quite a bit of sort of data reduction that happens in this whole process of model testing. And you will basically get 3 types of images related to the 3 types of sort of variables that you have in your model, which is right, like the beta values, the contrast values, and the t-values. And you will see in your working directory, you will see images related to each of these values. Right, so that directly corresponds to this to the variables in the GLM. And it's important to realize that although we worked out this example here and up to where you get like a t-statistics, actually for later analysis you use the contrast values, which are the actually contrast value is not quite right. It's the contrast times the beta values. So it's the other part of the equation. These are the ones that you will use for further analysis, and actually not the t-statistics. And the statistical reason is that you're in your t-statistics you're sort of dividing by your variance, and at later group level analysis you want to sort of incorporate variance across subjects, and therefore you use the contrast values. So we'll talk about that a little later. So in the example I gave, I basically just talked about the model in your fMRI analysis to be to this part, the presentation time of the stimuli, and then convolve with the HRF. Just to give sort of work out an example. In what you do in practice is you usually include some other factors too in your model. And for task-related fMRI, you might include, say, you often actually do that, is the motion parameters. So if you recall from last week, you have in this process of realignment, you also get estimations of how much each subject moved from scan to scan. You can use that information also to incorporate in your model to extra correct for motion. And there's other stuff you might want to include. Say you want to see if there are brain regions that relate to reaction time on a trial-by-trial basis. You might want to include reaction time also in your model. So you can include many different things. But I guess the basic point is that it's the example was just a little simplified in the sense that the actual model just does include a few other variables, either to control for like nuisance variables or to or they are of interest. And also, we're not going to really talk about this too much, but you could do a similar thing if you want to, for example, analyze your resting state fMRI data, which also is a really become really popular in fMRI research. And you could analyze your resting state data in a pretty similar way as your task fMRI, only your model would not be the onset then of certain stimuli, but your model, you would use the time series of some brain region of interest. So for instance, instead of saying, I want to see how one voxel fits the presentation of faces or houses, you could say, I want to see how well a voxel fits the time series of the amygdala, and in that sense, it means how well or how strongly these regions are correlated, or how strong they are connected. Right, so in a resting state analysis, you could do a similar thing as in task, but not to model the task response, but to model the connectivity. And you can even do, also within the task framework, you can analyze the interaction between the response in a region and the task related activity. You get like a PPI model. It's all more like this, more like advanced analysis. The basic is the sort of task fMRI, but it's good to realize basically that the setup is really similar, whether you do task fMRI, resting state, or some task connectivity. Right, you're always trying to sort of fit this model. Just the things that you include in the model differ from analysis to analysis. And you might, depending on the type of analysis, you might want to include different types of control factors. Often what they do, for example, in resting states include stuff like the global brain signal and a signal from white matter to sort of correct for non-neuronal fluctuations in your signal, etc. Right? There's a whole literature on these kind of things, but just to put it like sort of, I guess, the task fMRI in a little bit of a broader context, and to see that the models are comparable. A little different if you would use like structural MRI and say like a voxel-based morphometry analysis, because you're not really running sort of statistical analysis on the subject level. Then you do need to process the data a bit, especially to some tissue classification for your structural images. And the output there is say images of gray matter, volume, or density, compared to images of contrast values in your fMRI. Right, so that's a little bit more different. Actually, in a way, structural MRI and VBM is a little bit easier to process in that way. But the thing, I guess the main point is that no matter which sort of type of analysis, type of data you have, from here on out, you're going to use any of these images in a similar way. Like I said, this GLM, you basically run that at many different levels. So the example I gave was just for one voxel, right? As I already said, that is not really that informative, basically, right? Like how one voxel fits your model, because eventually you want to test something like if there's an effect, if there's this manipulation of, say, the phases versus houses has an effect in a group, or whether there's a difference in activation for phases compared to houses in different groups. And I guess you can look at it a little bit in this way, right? You run this model on a voxel, which you later combine into an image. You might have these images from different runs, so you might sort of chop up your task in shorter parts, say 10-minute parts. You might have like 2 or 3 of these, which you combine into a session. Session meaning, for example, if you have your subjects take some kind of drug and some placebo, right? You might scan them twice. So you have different sessions, and then that will lead to an image of different subjects, and you might have a bunch of subjects that are part of a group, and you might have another group, right, which you often have in psychiatry, some control group, some patient group, and then you want to do some group comparisons. Right, and the thing is that, so the idea is that you're running this model basically on each of these levels, and the most important thing is sort of the subject and the group level.
If you wanted to do it at different ages, what other variables would you need to control for? Because you talked about the different things, that noise and different things. So.
Yeah. If you would want to correct for age, then you would do that usually at the group level. So you would include the factor age as a covariate.
Okay.
Actually, let me see. Yeah, it's going to be on this slide actually. So what you?
Okay.
So yeah. So it depends a little bit. So for age you would do it at the group level because you just have one value, right, for each subject. Something as reaction time, you could even do both. You could say on a subject level, I want to put in the reaction time on each and every trial, and you could even at the group level have the mean reaction time as a covariate. So the different levels of it, how you correct for reaction time. But for something as age, where you just have one value per subject, you would naturally do that at the group level. So at this group level, your GLM looks a little bit like this. So your data now are not time series anymore, but there are these contrast values from all subjects. Right? So for each subject, you have like a image that contains for each voxel how well your model fitted that data, and these are going to be your observations now, right? And then let's just say your design matrix, your model, now is not the onset of stimuli anymore, obviously, but it might be something as a group status. So it's just a variable that has ones for your control group and say -1 or 2 for your patient group, right? Or it could be some individual difference, a variable like age or personality traits, if you want to interested in how these vary with brain regions. And this is much more closer related to what you're might be used to in SPSS, right, where you set up similar models to, if you're not looking at MRI data, but say at reaction times. This is a similar thing. Your beta values then are the contribution again of the parts of your design matrix. So in this case, that would mean like a high beta value would mean something that your group status, either being controls or patient, explains a lot of your data, which you often hope it does. And then and you would test these beta values in a statistical model. And again, it's always important to realize, like, you never fit this whole data set perfectly. You always end up with a bunch of unexplained variants. This is a slide from I stole from Will Penny, one of the developers of SPM, which sort of visualized this whole process a little bit, and it's kind of nice because it has some of the images from how it looks in SPM. So say this is for, it's like at the first level or subject level, you have these fits for different subjects. You have a design matrix, and we're going to look at it in the second hour a little bit, how it usually visualized in SPM. But it often looks as this sort of grayscaled square. It shows here these contrast images, so right, images for each subject that at each voxel have a value of how well one part of your model fitted the response better than some other part of your model. And you would use these contrast images at a sort of second level, group level analysis. In this case, maybe just to run a one sample t-test. So you just want to see, sticking with our example, if this was a contrast image for faces versus house, right? And you would test it at a second level, you might see all this across all this group of subjects, you have these activation in the visual cortex. Right, so this is a little bit of an overview how you go from subject level to a second group level.
So if you had, in this example, you've also got circles along with the faces and houses, and you would have a contrast image for each contrast you wanted to set up. Comes out of the analysis, right? So if you wanted to contrast faces with circles, that would be another set of contrast images SPM gives you.
Right, yeah. Yeah, and again, like this example is actually very simple. I just put in these two because you could often, and also the training data set has that, right? That's 4 conditions. So as soon as your number of conditions increase, the number of potential contrasts that you could set up greatly increases. So you have a lot more tests that you can do. And stick with the example, another thing you could do, for example, you could say, well, in which brain regions does either faces or houses have stronger activations compared to your like these just your circles, something like that, right? That would be another contrast you could set up, etc. Sort of depending on your research question, you have like a bunch of different tests that you can do on this group level GLM analysis. And again, this is highly similar to any analysis you run in SPSS. So if you say like if you just in general are interested in which regions are significantly more active for faces versus houses, you might want to run like a one sample t-test. That you're not interested in differences between groups, but if you are, then you might want to run a 2 sample t-test to test if your patient group differs from controls, and if you want to see which region correlates with symptom severity, for example, or age, or reaction time, then you might want to set up like a multiple regression model. So it depends a little bit on your question and how many groups you have, how many factors are in your model, what kind of test you do. But this is, I'm not going to talk about which test to choose in which case too much, because it's actually highly similar to how you would approach your data as if it were like a reaction time, just some behavioral data set. I guess whatever kind of test you do, what they all have in common, and this is something I want to talk about a little bit more, is that they again result in a statistical image, right? So you have that on the subject level, but it also happens on the group level. So you get like a image where each voxel represents either a, say, an F or a T or a Z value, depending on the statistical test that you do. And each of the test statistics have their own distribution, and they're related to p-values. Right? So regardless of the exact nature of your analysis, this will always sort of be your output, right? The thing that SPM or any other package will generate. And I want to talk about p-values a little bit more because it's somewhat of a tricky issue in fMRI. And sort of let's start off with just recapping the basic sort of framework that is used in fMRI, but in almost all or a lot of social science research. as the null hypothesis, significant testing, right? And it's probably familiar to most of you. The idea is that say you find some activation in some region, you want to sort of determine whether, statistically test whether there was truly activation in that region, and if there was, that would be a hit. Whether you think you see an activation but there's actually nothing, in which case you make a so-called type 1 error. So you end up, and this is what your p-value basically means, the probability that there is an effect, you observe an effect but there's actually no effect. Another option is that you sort of say, well, there's no effect, but actually there was, right, which would be a type 2 error, and there's a situation where you say, well, I didn't find any activation, and in reality, in sort of larger population, there is no activation in this region, and then it would be a correct rejection, right? I'm sure because most people are familiar with this framework, right? So the p-value then, and this thing that you always have to report to, so, declare whether a region is significant or not, is this probability. So it's saying that it's the likelihood of observing a certain effect, given that your whole data set was just noise, just random noise, right? And power is then the opposite of this type 2 error, because this is another important sort of statistical concept. So it's the probability of detecting an effect when there is a true effect. So it's the, in other words, the sensitivity of your analysis. Now, because these two things are often endlessly discussed in MRI because of the following problem, which is the multiple comparison problem. What you do in MRI and fMRI is you perform many of these independent tests, like independently, you run this GLM independently. And this greatly increases the risk of type 1 errors, right? So, as everyone probably knows, like usually you would use a alpha level, or which is called like an acceptable type 1 error risk of say 0.05, which means that if you would run some experiment a ton of time, then in 5% of the cases you would get, you would declare something as being active, or you would declare something as being a significant effect, well actually it might have just been due to noise, right? If you perform many independent tests, which you do in MRI, right, because you run this model like at least tens of thousands of times, then this error rate, this type 1 error, greatly increases. And this is always an issue in any kind of research, right? Like if you, like for some behavioral study, you have like a bunch of questionnaires, and you start correlating your questionnaire with some, say maybe some reaction time observation, 10 times, with 10 different questionnaires, you will increase the chance that you will just going to find something significant, which is actually a just due to noise. It's specifically an issue for fMRI because, again, what I started off with, it's a mass univariate approach, right? Like you test this model in, say, like 30,000 or more voxels, and even worse if you're in genetics, like you might run hundreds of thousands or millions of tests, right? Like, so if the number of tests becomes so immense, it's become really an issue. To give an example, if you use the sort of the common alpha of say 0.05, right? It's normal, what you set as a criterion to call something significant or not. You will find, this is given that all observations are actually independent, you will find sort of 1,500 voxels sort of to be active, even if it was just noise, right? Does that make sense? If you, which would be really bad, obviously, right? So you need to do something to correct for that. Basically, you want to correct your p-values to incorporate these large number of tests that you're running. And you can sort of split this issue of how you would do that in two parts. Actually, first is which method would you use, and I want to talk a little bit about that. So if you could do a Bonferroni test, a family-wise error correction, false discovery rate, I'm going to talk about it in the next slide. And then another sort of issue is where, or in other words, for which regions do you want to use it for the whole brain? Do you want to correct for all the tests that you did in the whole brain, or are you saying, well, you know, I'm actually not interested necessarily in every part of the brain, but maybe just a subpart of the brain that I'm really interested in, and I'm only going to correct for that part of the brain. So you have these two issues that that are important in this applying these corrections for multiple corrections. I think to keep in mind is that I guess familiar to everyone, but that there's always a cutoff. Say the more stringent, the more strictly you want to correct for type 1 error, it will always increase your type 2 error. I hope that makes people are familiar with that concept, right? Like, so there's always a trade-off here. So and people have, in my opinion, always the tendency to be very, you know, focused on this. You know, want to control for the type 1 error. But it will automatically means just by statistic definition that your type 2 error increases too. And you know, there's also people say you want to balance these two things as well as possible. But this is definitely sort of the key issue to try to establish like a good balance between these two. So the first solution, what you could do in terms of, you know, saying, well, if all these comparisons is just to do a Bonferroni correction, which basically states that if you have like a nominal alpha level of say 0.05, you just divide that by the number of tests that you do. It makes a lot of sense in a way, right? To incorporate all these tests, you want to be more stringent and you divide for all your tests. However, in MRI, this almost it's just not feasible, because if you would divide that, like your p-value has to be something like this in order to become significant, and that hardly ever happens, right? Because you get some crazy low p-value that's just not realistic to observe. In other words, you would need like a huge effect size to declare something significant. And it's also this is actually more important. The reason it's too conservative is because not all voxels, not all observations are independent, and the Bonferroni correction is only really valid, only sort of necessary if all those observations are independent. And fMRI and a lot of other data sets too, that goes for behavioral data too, you know, one variable relates to another. And I showed a similar plot like this before, but now say imagine that this was a slice of test statistics, right? So this is a slice of the brain where each value represents like a t-value, right? Does that make any sense? If you would just take one part of the brain and say this little thing, or say this thing here is a t-value of maybe 2, and well, this one here has something like 0.5, right? So what this shows is that there's a certain type of so what they could say like smoothness of your data, right? So if I would take this example, if this little voxel has a high t-value, its neighboring voxels are more likely to also have a high t-value, right? This is the reason that this is the case is partly due to one of the pre-processing steps, if you recall from last week, where you actually smooth your data. So you're trying to spread out the make sure that your data is sort of correlated in a bit. And the fact that these observations are not completely independent, or sort of visually that this is not like an entirely sort of spiky thing, but there is some, you see some hills, so to say, in this image. Also means that a Bonferroni correction would be too conservative.
Let's say anatomically. So you smooth it to make sure the voxels next to each other are like
Right.
each other, but it's like
Of course,
two voxels cover the amygdala, so all those voxels should act more like each other than not. So
exactly, yeah. Right, so Bonferroni would be, in theory, would be, say, well, it's possible, but it's just, for this reason, it's too conservative. So what people often do it, well, yeah, there's sort of a few different ways. So the second solution is use some voxel level correction method. So you're basically trying to estimate how many independent tests there actually are, and to correct for that. So not necessarily correct for all the tests, so you have 30,000, but you're trying to, by a statistical procedure, trying to estimate how many tests you should correct for. So this one might be a lot less. Say you really should only correct for 5,000 independent tests. That's a way to look at it, right? So you correct your p-value for basically for this estimated number of independent tests. And then what you do, you just say, well, anything above this threshold, which would be a p-value threshold, which also corresponds to a t-value, to some test statistics, I'm going to call significant. If you look at this sort of image, so suppose you have, again, take one slice of the brain with all statistical values, and you sort of lay it out in this two-dimensional way, or actually one-dimensional way, where you where like each little part here is a voxel, and here it's the your test statistic value, right? Then you're just going to say, well, I've estimated the number of independent tests that corresponds to a certain p-value. I've corrected my p-value, which in the corrected p-value corresponds to some t-value, and any brain region that has a t-value above that, I'm going to call significant, right? So in this case, if this is your distribution of effect sizes of t-values, you're going to say, well, this voxel is significant, right? Because it exceeds this threshold that I've determined by correcting my p-value, which corresponds to the t-value. Yeah. And then what you would do statistically is say you would reject the null hypothesis at this voxel. So you would say, well, for this voxel, it's really unlikely that this voxel would be active if my whole data set would just be pure noise. So I'm going to call this voxel, and the brain region in which this voxel is, I'm going to call this significant. There are two ways how to establish what that exact p-value threshold, which again corresponds to a t value or some other test statistic value, is done. And the reason I want to mention this is because you're going to see this in your SPM tables. You're going to see all these terms are coming back, so to say. One way is to establish a family-wise error rate, which is the rate at which you have one or more false positives. So you're trying to correct for this, they call like the family of statistical tests that you're running. I will have an illustration of how that works in a little bit. Another common way is to correction method is the so-called false discovery rate, which always looks really similar, but it's a little bit different. You say that based on the number of voxels you're going to declare active, you try to estimate how many of those are false positives. And you call that the false discovery rate. So these are two different methods to correct for all the statistical tests and to try to establish what your corrected p-value should be. And I just want to give, again, these slides are from Tom Nichols' presentation, a little bit of an illustration how these different methods have a different effect on your data. Because I think it's important to sort of realize when you're looking at your results table. So suppose you have just these are just images with pure noise, right? Like they're just randomly distributed noise. And you have here images with signal. So you have, like here in the middle, there's some signal, these brighter spots, right? If you add these two, your image, and again, this is two-dimensional, right? Your actual image, fMRI image would be three-dimensional, just for this example, it's a two-dimensional image that has some signal here in the middle and some noise outside. Does that make sense? Yeah? If you're going to set some threshold, right, you're going to say, well, I have all these, all these values at each voxel, and I'm going to set some threshold of what I'm going to call significant, without really doing any correction. You might get something like this. So now your image is sort of what we call binarized, right? Like it's either, you call it either significant or not. In this case, significant will mean a little white dot and black will be non-significant. So what you would see is that if you look at all these different options, you're, by not really using the correction method, you're going to keep most of the stuff that was originally signal, so in the middle. But you're also going to get a lot of stuff outside this little red border, which was, right, which you knew in this example, was just noise. If you control the, what it means to control the family-wise error rates is that if you, and in this case at a 10% level, is that if you would run this thing 10 times, right, where you have these 10 images here, is that it's to be expected that in one of these 10 times, and in this case, you would get at least one voxel, one part of the brain that you're going to call significant, while it's actually not.
You actually got a 2 in that one.
Yeah, it's 2. Yeah, so it's at least 1. So, yeah. Right. So on the long run, this is what the family-wise error rate means. And just visually, even if you like sort of forget about the details of how that works or what it does, what you can see if you compare this row, right, to this row is that you can see that this is a lot more conservative method, right? Because we know, and again, this is the stuff that you in reality don't know, but in this case, in this example, you know that anything within this red circle is actually activation. So in an ideal world, right, you would call everything outside would be black and everything inside would be white, right? That's how your ideal statistical test would be. And of course, it doesn't happen, so it's some trade-off here. And what you'll see here is that, you know, in each case you're saying, well, there's a couple of these parts inside this red circle where we know that our signal we declare it statistically significant, but also a lot of stuff which we should declare statistically significant, we don't, right? But the good thing is, right, there's very few times that, like on this part outside of this red circle, we call statistically significant. If you compare that to the false discovery rate, it's just a different type of test statistic, or a different way of correcting your p-value. And what this does is say, well, in the long run, so average over all those 10 images, 10% of the time, 10% of my observations, 10% of the things I'm going to call statistically significant are actually not. Right, so, and what happens in here, if you look at that, is that you get a lot bigger proportion of the stuff inside those red circles, right? So you're picking up a lot more of the actual signal, but you're also making more mistakes, right? You're also picking up, you're more often declaring stuff that's outside of your actual signal statistically significant. Right, so, and the important thing to recognize is these values are identical. So basically what it means is that sort of controlling for the family-wise error rate or using a false discovery rate at the same level leads to a different outcome. And it's usually the case that the false discovery rate is a more lenient way of correcting for your for these multiple comparisons than the family-wise error. And again, even sort of disregarding any of the details of how these methods work, it's sort of important to realize that if you're looking at your results tables from SPM, it might be the case that something is significant with an FDR correction, but not with a family-wise error correction. A third solution, right? So we have the Bonferroni with the voxel level corrections, is to use what they call a cluster level correction. And this is a two-step procedure. So what you do is you first establish this sort of alpha level, this p-value, that's a critical p-value, again corresponding to some t-value, that any of the activation in your brain should minimally have. But the second part of it is to also say, I want this this activation level, so to say, to spread for a minimum amount of space, right? So it has to, you know, if it's just one voxel, I don't really think it's activation. I want to say, well, it should at least be 10 voxels. My activation pattern should at least be 10 voxels wide. And the reason to do it is because you're losing some spatial specificity, right? If you start saying, well, you know, if your clusters become larger and larger, you're not really necessarily sure anymore whether it was some activation from, say, from this little nuclei in the brain or some other nuclei, but depending on how this activation is spread, you might be more sensitive to pick something up. In other words, you're more, you make less type 2 errors, you have more statistical power. And an illustration of this, of how the cluster significance works, you can see here. So this is the same sort of, you know, distribution of your test statistic values that I showed before. And right, so here this is like the x-axis some you know space, so you have all your voxels lined up. This would be the y-axis would be some test statistic value. So you would set a certain criteria for what would be like the minimum activation level to have, and you would set a criteria for how large it should be. So you can see the difference here, that in this case, this is the same, right, same data as this one. So here we call this voxel significant, but these ones we didn't call significant because they didn't pass this threshold. But in this case, we're doing the opposite. We are calling these voxels significant because they both pass the threshold and pass this, you know, this cluster extent. But actually, this voxel that we determined significant in the voxel-wise approach, it's not significant because it's like it might just be one voxel, right? So in reality, it's not always like as either or as this example, but this is how to think of it, right? So depending on what method you use, you might end up with different brain regions. And there are a bunch of different implementations of cluster level statistics Yeah, it's not really worth, I guess, to go into the details, but like each package basically has their own sort of way how to implement these things. And it's always a little bit tricky. There's a lot of literature on this, on like how to sort of the combination of how to choose your you know, your initial threshold level and what your and then how to determine what the spatial extent of your cluster should be. I think we could put on some papers on this topic on the on our website. A fourth method, it would basically to say like I'm not going to bother about any of these sort of correction things, and you'd be surprised because this is actually a really common thing to do, right? Because you know all these correction methods, they're difficult, complicated, etc. So I'm just going to say, well, for example, use a
help me find what I want to find.
Yeah, I use an uncorrected threshold of say 0.01, right? So you're sort of disregarding this whole process. Say like I'm going to be a bit more conservative than saying just 0.05, but so I'm going to drop my p-value a bit, but not really going to do any trying to estimate my false positive rate. And again, like this is actually really a common thing to do. The problem is you get a much higher false positive rate. So there's this paper out on if you would use this type of threshold, your family-wise error would be more in the range of 0.15 to 0.4, which is important to realize, right? So if you're thinking that if you're applying like the threshold like this, you might actually not be testing at a level of 0.05, but more at a level, a corrected level of 0.4, right? And if you compare that, you would never publish a behavioral data paper where you're going to call any statistical test that is below, you know, a p-value of 0.35 significant, right? That would never happen. So it's important to realize that using this kind of stuff might mean something like this. And it would be fine if you would say, okay, well, it's just a little bit more lenient, but you know, less type 2 error, more statistical power. Another problem is that what the exact sort of family-wise error level is, or can be different for data sets. So a p-value of 0.01 is not comparable across different papers or across different data sets, which is another reason why just using an uncorrected threshold, it's somewhat fine in a way if you're exploring a little bit in what's going on in your data, but it definitely has disadvantages. And I think it's just a really practical thing. If you're writing a paper, you know, it's more and more likely that reviewers will sort of not buy it if you don't apply actual correction methods. So it's still really common, but it's tricky to not do any correction. Last point I want to make is that you can, so you have these different type of methods that you can use to correct for your the multiple comparisons. Another issue is, you know, do I want to do these corrections for the whole brain? Again, maybe those 30,000 or more voxels, or do I restrict my corrections for a specific region, what they call a region of interest, right? And we always love the amygdala in that case. This would be the advantage of like being restricting your sort of search space is that you end up with a lot less tests. So, for example, for amygdala mask, you know, we might have like 500 voxels, which is, you know, you greatly reduce the number of tests and the number of tests that you need to correct for. So it has great advantages in that way. Like if you know which brain regions you're interested in, to say, okay, I'm just going to correct for that. And then there's sort of two ways how you can do this type of analysis. One would just be to say, still use like a sort of a voxel-wise analysis within this region, say for the case for the amygdala, within each of these 500 tests. And another way would be to say, just say extract the data from this whole region and calculate the mean, right? And then you have like a mean amygdala response. And then again in this case, you're sort of only left with one test, which is, you have to reduce this whole problem, which you start out to do whole brain analysis tremendously, right? Downside is if you would do this, suppose like one part of the amygdala responds a little bit different than another part of the amygdala, and you take the mean, right? You might sort of average out any effect. So it's difficult to say what is the best. It really depends on the situation. I guess usually people just do all and see what comes out. Shh. That's the way it is. There's two different things that are really tricky about this type of analysis. One is that, and actually these are really, people do a lot. If you have multiple ROIs, if you have multiple regions, what you often have, say, okay, I'm not maybe interested in the whole brain, but I'm interested in the amygdala and the insula and the medial prefrontal cortex and the caudate and a bunch of these regions. And you want to do this region of interest analysis, you should correct for all your brain regions at once. If you start sort of first correcting for only the amygdala, and then you run your tests and correcting only for the insula, you still ended up running like all these tests again, right? So if you want to do this sort of proper ROI analysis, you should combine all the regions you're interested in and correct for all of the voxels within these regions. And you would often see that people just, might say like you have these 10 different regions of interest and they test for each of them separately. Another thing to consider is that this type of analysis is only valid when you sort of truly a priori have selected these regions. If you first have a look at your data, right? Maybe you do a whole brain analysis. You see something popping up in the amygdala, but not quite significant. And then you start running a ROI analysis with just the amygdala. It's not really a valid test anymore.
What if you say, okay, there's a lot of areas that look like they may be hot. I did my whole brain analysis, and now I want to go back and I'm going to pick the highest 5 areas of interest.
That would be okay if the test that you're doing is called orthogonal to the way you selected that data. So suppose, to keep with this example, right, suppose you would run this, you have to experiment with this phase in the houses and you end up with a bunch of regions that show stronger activation for phases versus houses, right? Like say the amygdala, some other frontal region. If you say like, okay, now I'm going to focus on these, say we find 5 clusters from this whole brain analysis. Mm-hmm. If you would then focus within these regions on whether there's a difference between, say, your patient group and the control group, that would be fine in a way. Right? That test of differences between group A and group B would be, as they call, orthogonal to the test that you did to determine which regions are significant across the whole group. If that makes sense, right? Like, so if the test, if you say you would find a bunch of regions based on actually the test you're running now is patient group A versus patient group B. You then find a bunch of clusters, you extract them, and then start to say maybe to correlate with symptom severity. The test is not really independent anymore because you already selected stuff that has a stronger activation in your patient group to begin with. Okay. Right. Yeah. So. There's actually a lot, like on this whole issue, there's quite a lot of debate because there are, but in principle, you can do it, but it becomes a little, it really depends on what kind of test you're doing, if it's sort of valid or not. I should, I have one last slide. What I always sort of think of with sort of in these two considerations, so if you look at the different types of correction methods that you have, right, I talked about the Bonferroni correction, family-wise error, false discovery rate, cluster correction, or maybe just use an uncorrected threshold. And approaches as like using sort of regions for which you correct, like the whole brain or just a certain region of interest. I always think of it a little bit in this sort of, two-dimensional space, right? Where you can be really stringent on your alpha control, so you type 1 error, then you would use Bonferroni, probably too strict, but you could do that. You're less sensitive, right? Like you did less sensitivity, meaning a low power, many type 2 errors. Quite often you would not find something active while it actually is. If you're more lenient, use an uncorrected threshold, you get the opposite, right? Higher sensitivity. If something is active, you will more often pick that up, but you have higher power, but you'll also more often declare something significant that's actually not. And then sort of the other axis in terms of which regions, for which region to correct, you'd say whole brain, maybe do more in an exploratory analysis. But in a way it's also more objective in the sense that you don't have to justify why this region, why not another region. It's obvious that that there's little debate on whether the regions you choose are valid, whereas a region of interest analysis you would use in a way more for confirmatory analysis, but it's also subjective, sort of, because there's so many options that you can choose, there's so many ROIs that you can choose, so many different ways how you can use an ROI analysis. And so, like, ideally, sort of the most clean way to analyze your data would be to be somewhat here, right? Do a whole brain analysis and use a pretty stringent way of correcting your data. But probably most papers are over here somewhere, right? Like they would use an ROI analysis and be a little bit more lenient, and that's just because of that the effects you find might not always be so strong. I think it's sort of good to sort of like realize these sort of trade-offs between these things a little bit, because it's often sort of the decisions that you have to make once you've analyzed your data.